Okay, we are going to proceed now with our keynote speaker today, Joe Romm. First of all, as a means of introduction, Dr. Romm is a senior research fellow at the University of Pennsylvania Center for Science, Sustainability, and the Media, and the author of two newly released papers on carbon dioxide removal. Romm holds a PhD in physics from MIT and has authored countless articles and 10 books in the areas of climate change, clean energy, and communications. In the 1990s, Romm spent 5 years working on climate solutions at the U.S. Department of Energy. For 3 years, he helped run the Office of Energy Efficiency and Renewable Energy, ultimately serving as acting assistant secretary, where he oversaw $1 billion in research and development and demonstration of low carbon technologies. This included renewables, building efficiency, industrial decarbonization, energy storage, bioenergy, hydrogen, and alternative fuel vehicles. In 2009, Rolling Stone named him one of the 100, quote, people who are reinventing America, and Time Magazine named him Hero of the Environment and the web's most influential climate change blogger. Romm was chief science advisor for the Emmy-winning docuseries Years of Living Dangerously. His Oxford University Press book, Climate Change: What Everyone Needs to Know, third edition, was called the best single source primer on the state of climate change by New York Magazine. And so I'm very pleased to have Dr. Romm deliver remarks today about his view of the role of carbon removal in the climate policy ecosystem. And so the floor is yours, Joe.
Well, thank you, Will, for that introduction, and thank you for inviting me, and I appreciate everyone who has come to attend this conference. The good news is I won't be using PowerPoint because the University of Pennsylvania Center for Science, Sustainability, and the Media, where I am a senior research fellow, has released two papers by me this morning. The first is Why Scaling Bioenergy and Bioenergy with Carbon Capture and Storage is Impractical and Would Speed Up Global Warming. And the second is Why Direct Air Capture and Storage is Not Scalable and Net Zero is a Dangerous Myth. And I will post the links into the chat so that I think I've done this to everyone in the chat. Before I dive in, I do want to comment on there's a New York Times piece out today on the first direct air capture system in the United States. And it's really one of those credulous pieces that does not manage to talk to anyone who would explain at least the side of why this is really a very problematic thing to be doing. And let me start by saying that the world desperately needs as much carbon dioxide removal as possible. That's because we have kept increasing emissions for the 3 decades since scientists have started to warn us with increasing urgency that we have to decrease emissions. But unfortunately, the 3 most prominent CDRs, carbon dioxide removal strategies, direct air capture, tree planting, and bioenergy with carbon capture and storage, either cannot or should not be scaled up significantly. And that does mean that right now net zero is really a trap that could easily delay or deter real emissions reductions in the next decade or two. And indeed, one 2020 study argued that if in fact carbon dioxide removal does not pan out, but we count on it to pan out, that could result in an additional temperature rise of 1.4 degrees Celsius, 2.5 degrees Fahrenheit, above the the 1.5 degrees Celsius target. So we're talking about ultimately 3 degrees Celsius warming in that scenario. And related to net zero is a lot of people have argued that if we had enough carbon dioxide removal, we could conceivably overshoot a temperature target by mid-century, and then turn global emissions massively negative to quickly cool back down. But this and this, by the way, is in many of the climate scenarios that are in the literature, and that the Intergovernmental Panel on Climate Change puts in their reports. But really, this is dangerous magical thinking, because that requires a even greater amount of scalable CDR, because you have to go well below zero, to actually start relatively quickly cooling back down. And unfortunately, I think so there's the upcoming Conference of the Parties meeting in Dubai at the end of this month, which is the UN-led global effort to avoid catastrophic climate change. But it is also really, resting a great deal on this notion of net zero, which is intimately connected to carbon dioxide removal. I mean, I think the key point is, humans spew some 50 billion tons of CO2 and other greenhouse gas emissions into the atmosphere each year. And the science is pretty clear that we need to bring those emissions down to zero by mid-century to avoid catastrophic heating of the planet, and even worsening and ever worsening damage to human civilization. And net zero is the idea, the hope, that we don't actually have to reduce global emissions anywhere near zero, because various carbon dioxide removal strategies that are not yet commercial will scale up rapidly to permanently suck the equivalent of our remaining CO2 emissions out of the air each year, perhaps by 10 billion tons a year or more by mid-century. Now, in 2022, last year, the world's leading climate and energy experts, of the Intergovernmental Panel on Climate Change, put out a 2,900-page report on greenhouse gas mitigation. And they looked at all the emissions pathways in the scientific literature and concluded, quote, CDR options in pathways are mostly limited to BECCS, afforestation, and direct air CO2 capture and storage, DACs. But, if you read the whole thing closely, the whole report closely, it's clear they're pretty skeptical about the scalability of those strategies. And that becomes even clearer if you look at the scientific literature of the 2 years since that report stopped looking at the literature. And it's also clear from new modeling that I present in the papers from the modelers at Climate Interactive, who have this En-ROADS model that allows you to look at the impacts of different climate strategies. And I think it's important to say that not only don't those things scale, but if you try to seriously scale up direct air capture, that would be a tremendous misdirection of renewables and resources. And if you try to scale up bioenergy, that would just make things worse. It would actually speed up global warming, because really speeding up bioenergy these days means speeding up the chopping down of trees, and it's just not much different analytically than deforestation. So, I'm sure I'm telling people, a lot of what they already know in terms of the basics, but I do try to cover some of the basics just to bring everyone in the audience into the same place. The thing about direct air capture is that, you're generally using, if you want to, try to reduce a significant amount of emissions in a relatively, short amount of time, you need a huge array of fans to pull the CO2 out of the air and run it by, a sorbent, something that will absorb it. And the system uses that to capture, pressurize, transport, and then inject underground the CO2. And all of this requires a huge amount of energy, because CO2 is incredibly diffuse in the air, 420 parts per million. And you must filter a Houston Astrodome's worth of air to get just 1 ton of it if the system were 100% effective at capturing CO2. And I think the key other point, as the National Academy of Sciences explained in their 2019 report on negative emissions technologies, that direct air capture is somewhere in the neighborhood of 5% to 10% efficient, depending on which strategy you use. And so the combination of the tremendous energy use, the capital cost of trying to suck in and capture all of that diffuse CO2, and then compress it and transport it, means you have very high costs. And the New York Times was reporting that the new CO2 DAX plant in the U.S. has got a $600 to $1,000 a ton cost, which has basically been the cost that has been offered, I think, by most of the direct air capture companies in the past 5, 6, 7 years. Now, in a June talk, the CEO of Climeworks, which is one of the direct air capture industry leaders, at a conference on direct air capture that they were sponsoring, according to Bloomberg, told the crowd his company could see its prices remain as high as $300 by 2050. So, that's quite a remarkable statement, I think, and should be taken, quite seriously, particularly since there's other recent studies that make a pretty similar point. So this is going to be expensive, and we hope to get it well below $300, but sitting here right now, I don't think anybody should be basing public policy on the notion that this is going to become affordable anytime soon. And, two direct air capture experts noted last year that even if we could get down to $100 a ton, which they acknowledge would be pretty hard, it would still cost $22 trillion to reverse warming by only 0.1 degrees Celsius. So, this is a very expensive and inefficient and costly way to pull CO2 out of the air. Now, I think what has been missing from this discussion, public discussion, although it's certainly not missing from the scientific literature, is that direct air capture only lowers CO2 emissions if it runs on vast amounts of renewables or nuclear power. But a July 2023 analysis found that coupling direct air capture systems to intermittent renewables is typically not favorable for low costs. You need high capacity factors, very high capacity factors, and that's why most people who actually do modeling of this don't use intermittent renewables, at least in peer-reviewed papers, because the numbers are very, very hard to work out. And even this July 2023 paper, which looked at 4 different low-carbon scenarios and the electric grid to charge 4 different possible direct air capture systems, ultimately at the end says, we're going to model this running on nuclear power, and the only way to get low costs out of that is if you assume, that nuclear power suddenly, becomes like half as cheap as it is now and goes on a much sharper learning curve. So the point is that because you're using renewable power for an expensive and inefficient system, the question is that the carbon-free power could have been used to directly replace the CO2 emissions from fossil plants and cars more efficiently and cheaply. And so this is a really important point. There's a 2021 analysis that said only when the region's electricity system is nearly completely decarbonized do the opportunity costs of dedicating a low carbon electricity source to direct air capture disappear. And indeed, another analysis basically made the same point, that using renewables to power electric vehicles to replace gasoline vehicles is far more cost effective at reducing CO2 than using them to power direct air capture. And I would note that again, you make the same point on electrifying building heat for buildings and industry, which is heat pumps are incredibly efficient. And in fact, they're so efficient that they actually generate cost savings themselves when you use them to replace, natural gas boilers. So it is going to make more sense to use renewables with heat pumps to displace fossil fuels for heating than again, using the renewables for direct air capture and paying a huge amount of money for a direct air capture system. And, and again, this is not a new idea, and I don't understand why it's not talked about more, why the New York Times could write a whole really long piece on this subject without mentioning this fact. And to give you an idea, way back in 2019, the National Academy of Science, U.S. National Academy of Sciences, did a big 2019 report on all NETs, negative emissions technologies, and they held a series of public workshops and meetings to inform their deliberations. And their report notes, quote, "The committee repeatedly encountered the view that negative emission technologies will primarily be deployed to reduce atmospheric CO2 after fossil emissions are reduced to near zero." And just to be clear, fossil emissions are not going to be reduced to, on the current emissions trajectories of every major country in the world. The fossil emissions in the world are not going to come close to zero until after 2050. Unfortunately, that's just the reality. Hopefully, things will turn around, and all the countries of the world will suddenly get a lot more ambitious in their policies and actions rather than just their promises. And certainly, I think all of us are working towards that end. But I think we have to be realistic here. It is going to be a very long time before direct air capture is not a costly misallocation of renewables. And this is a lot of renewables. This is really a lot of renewables. There was one 2020 review article that looked at all the life cycle analyses and noted that by one estimate, renewables powered direct air capture would require all of the wind and solar energy generated in the US in 2018 just to capture 1/10 of 1 gigaton of CO2 per year. And remember, we have 50 gigatons, so that is 1 part in 500, or 0.2% of total emissions. So you are going to have to use a lot of renewables. And so, again, not a good use of renewables for decades. Another interesting case is bioenergy carbon capture and storage. Which is really, I've talked to a bunch of people, it's really the first quote unquote solution to climate change that was just invented by climate modelers. It was not proposed and advocated by people who understood bioenergy. It was really created by the climate modelers over the last 2 decades, as they realized it was going to get increasingly hard for their models to get emissions low enough to stabilize at 1.5 degrees Celsius. So they needed to come up with a lot of negative emissions technologies, and this is one that they came up with. But the bottom line is, when you do the analysis correctly, if you scale up bioenergy and BECCS over the next several decades, all you're going to do is increase CO2 emissions and global warming for several decades, and net cooling is not going to occur until 2100 or beyond. So, that's sort of problem one. The other problem is land. If you were to try to scale up bioenergy carbon capture and storage to get to just 2 to 3 gigatons of CO2 per year at a steady state, that would require a land area the size of India, 800 million acres. And the reason this is the case is because in places where bioenergy has been scaling up, like Europe, wood has become the input of choice to burn. And wood is, quote, likely to remain the biomass fuel of choice for electricity generation and heat at least for the next 10 years and probably longer. And I'd be happy to take questions on that. But fundamentally, this notion that has been promoted that we're going to use residues from forests or agricultural waste or that sort of stuff, waste products. That's how we used to do it 15 years ago, before Europe and others decided they needed to do this rapidly at scale. And if you're going to do it rapidly at scale, you're going to need something that's very dense that you can transport over long distances. You're going to need something that's very uniform and standardized, and that's why everybody switched over to wood pellets. And those wood pellets are, made in plants that take, real wood and trees and all that, and turn them into pellets. And that's what everybody does, and that is what everybody has been doing. And so the thing is that when you run bioenergy on trees, you have these two problems. The first is that every year you're cutting and burning more and more trees, and you just result in a huge net increase of CO2 emissions. This is the growing carbon debt that is not paid back for several decades. The point is, you cut down a bunch of trees, you dry them out, you turn them into pellets, you ship them across the ocean or long distances, you put them in a pelletized, a bioenergy system, you burn them. Right now we don't capture the emissions. If you cap the emissions, that doesn't change things very much, as it turns out, because the capture system uses so much energy that it just reduces the efficiency of the whole system, like 30 to 40%. You're just releasing a huge amount of CO2, right? You're releasing the CO2 from the tree trunks and all the stuff that you cut down, and all the energy you used along the way, and then you're releasing all the energy when you burn the biomass. And you only get that back when the seedlings that you plant, grow to somewhere near maturity, which takes, a couple of decades or longer. But if you're scaling up bioenergy, then you're just scaling up, cutting down trees, and every year this debt grows. Again, the literature is quite clear on this. So you don't even stop increasing the carbon debt until you stop scaling up your harvesting of trees, or any biomass for that matter. But we're using trees, and as a result, CO2 emissions rise year after year after year. During this entire time, the planet warms up during this time, and it won't cool down until next century. I like to say that scaling bioenergy and bioenergy carbon capture and storage is not a climate strategy. It's not carbon removal. It's a lot more like deforestation. A review last year by the European Academies of Science Advisory Council noted that it must be pointed out that in a world where land is scarce and subject to competing demands, it is important to recognize that the area of land required to generate energy from biomass is 50 to 100 times larger than for solar and wind. And thus land usage for bioenergy is inefficient, right? Because photosynthesis is great, but it's an incredibly inefficient way to turn sunlight into electricity. Or I should say into energy that you then, have to turn into electricity. Direct air capture and bioenergy, they have a combined problem, which is that the scale of the carbon capture and storage challenge is enormous. Again, not talked enough about, although it's in the literature. If you want to sequester, if you want to capture and store just 3 gigatons of CO2 emissions a year, 6% of total global emissions, you got to capture, transport, and store a volume of compressed CO2, and you have to compress it a lot just to get to this number, this volume of CO2 is greater than the amount of oil extracted each year by the global oil industry and the entire transportation, and oil delivery system of the world, which took a century to develop. So the notion that this is going to happen in a couple of decades is, pretty. It would be the greatest achievement in all of human history. And again, it just gets you 6% of global emissions. So carbon capture and storage is important to pursue, but again, it's not the silver bullet. And, there was an analysis from Princeton which said that carbon capture and storage could require more than 60,000 miles of new CO2 pipelines in the United States alone. And we're in an environment where it's increasingly difficult to build a single new pipeline, and a 1,300 miles of planned CO2 pipelines were just scrapped last month because people don't want these CO2 pipelines going through their land. They don't like when eminent domain is used to seize their land. They're fighting it. And it's going to be it's going to be very hard to build thousands and thousands of miles of pipeline, but 60,000 miles, that's again, that is a very big challenge to take on. And it's worth noting, carbon capture and storage, not going to talk a lot about it, but it's not yet proven commercially scalable. The US has been trying it for a couple of decades now, a lot of government spending, and by and large, we're still struggling with demonstration projects that don't deliver what they said they would, don't come in at time or budget. So we have a lot of work to do to just solve the CCS problem. And to be honest, and again, this is in the literature, if we do solve the problem and see carbon capture and storage becomes commercially scalable, you should just put the CCS systems on coal or gas plants, right? That's going to save more CO2 for a lot less money than putting it on either a direct air capture plant or the bioenergy plant or the direct air capture system. So, and let me just, chat a little bit about trees. Planting trees is not scalable. And that's because, again, trees, you have to plant a staggering amount of trees over huge tracts of land to make a small difference. And again, the Climate Interactive has published this modeling. It was in the Washington Post. If you plant 1 trillion trees, that would remove, at best, optimistically, 6% of the total CO2 needed to keep warming from rising beyond the 1.5 degrees Celsius limit, which is the tough goal that's in Paris, compared to the goal that everyone could agree on was well below 2 degrees Celsius, although they're similar. But the point is that would require more than 2 billion acres of land, which is to say more than 2 billion football fields, which is larger than the area of the lower 48 states. And then you want to add bioenergy, carbon capture and storage on top of that. That would be another 800 million acres, the size of India. So that's a lot of land. And studies already suggest the world's going to need over 1 billion acres of good agricultural land just to feed everybody in 2050. And the UN Food and Agriculture Organization in 2021 published a big report saying agricultural systems are already breaking down, and quote, there is little room for expanding the area of productive land. So we don't have a lot of excess land in the world. A 2021, the lead author of a 2021 Nature study explained also, this is something we've learned in the last few years. It would be a mistake to plant trees in natural grassland and savanna ecosystems. Why? These grassy ecosystems, with very few trees, are also very important for storing carbon in soil. So the point is, you can't plant trees just anywhere, just because there's an open area of grassland and savanna. If you want to dig up that land to plant trees or seedlings, saplings, You got to calculate the lost CO2 that was in the soil. These are complicated analyses, but the point is, you can't just say, oh, there's all this land here, we're going to plant trees on it and solve the climate problem. That's not the way it works. And indeed, at this point, I just ask people who are advocating massive tree planting or bioenergy carbon capture and storage, tell me where the trees are going to be planted. Because most of the supposedly empty, unclaimed land targeted for tree planting is actually claimed and used by indigenous peoples and local communities. And seizing it to plant trees would perpetuate centuries of injustice. And everyone, I think, listening, everyone in the climate community, everyone who cares about global warming has made it clear that we are not going to solve or try to solve the climate problem on the backs of indigenous peoples and local communities who have been suffering from having their land taken from them for centuries. So this is a very serious issue. I don't think anybody has seriously looked at just how much land is really available and what would be the best use of it, because you got to feed the world, number one. And that's basically what I had to say. There was an article in 2021 published in The Conservation by three leading scientists, including Bob Watson, who was former head of the Intergovernmental Panel on Climate Change. And they said, and they called net zero a dangerous trap. That was the title of the piece. And the line in the piece says, in private, scientists express significant skepticism about bioenergy, carbon capture and storage, offsetting, and net zero. And but the point is, this is not something that has to be expressed in private. There's a lot of recent studies, a lot of recent analyses make clear that all of these supposed climate solutions deserve a significant skepticism. And as I say, we do need to figure out every carbon capture system that could work, but we have a long way to go, before we get to the point where someone can say this is going to be a major contributor to solving this problem by 2050. Thank you very much.
All right, thank you very much, Joe. So we've got some time for some questions and some discussion, and so I'm going to take a number of the questions and consolidate them into kind of the elephant in the room, right? If you acknowledge, I think all of us acknowledge that because we haven't gotten our act together in terms of traditional mitigation, we're going to need large amounts of carbon removal, right? At least on paper. If these approaches are DOA in your mind, and I don't think I'm unfairly characterizing that, what other carbon removal approaches, if any, do you think are worthy of further scrutiny?
Well, look, I do think that there are strategies. I think biochar, and I think things related to soils are important to pursue. Certainly, there have been some promising studies, and there have also been studies casting doubt. The tricky part with soils, right, is, the thing about the three that I discussed, and the reason why they get discussed a lot and why they're the most analyzed, is because they have been viewed as the most measurable, quantifiable, and trackable. Because ultimately, if you're going to monetize something, right, you have to be able to measure it and monitor it over time. And that is always a challenge with soils, to calculate what the CO2, the carbon in the soils was before you did your thing, what did your thing do, and then over time, what's happening, because you can't just say, oh, I put a lot of carbon in the soil. You got to say, well, what happened to that carbon, and how permanent is it? And by the way, I think carbon in soils is probably more permanent than carbon in trees, because trees can burn down. So I think those are worth looking at. And obviously people are doing them. I don't want to say worth looking at. I think that some of the strategies about weathering and the oceans are worth pursuing. They're all going to have. The question is, can you get the combination of permanence, scalability, measurability, and trackability, monitorability over time, right? You need all four of those if this is going to be a something that rises to the level of, oh, this could have a big impact by 25, and it could be turned into a monetizable market, right? Because there are things we should do because they're probably going to help us, right? We should do them. But if you can't say this is how much and this is what it's going to be in 50 years, it is going to be hard to get people to pay you, per ton, right? They may say, oh, I'm going to support this, but it's different. That's different from saying I've got a solution that we can bet the future of the planet on, right? That's what we're talking about here after 35 years of dawdling.
Okay. All right, let's go to some of the specific questions in here. Let's see, let me move up a little further. Okay, so you've addressed ocean, right, as one that should be looked at, I believe. So I'll move past that question. Question is, someone who's worked in the agriculture industry, what about burning biogas emitted from the fermentation of agricultural residue? Is this type of bioenergy suitable for scaling and helpful in the long run?
Well, I think the short answer is anything that's relying on residue is quite hard to scale. And that is why Europe basically had to abandon residue when it decided that it was going to scale up bioenergy. And bioenergy has been, in Europe tremendously scaled up. The thing about residues is it's left over from something else that you did. By the way, there's different types of residues, right? There are residues that you can't use for anything, and then there are residues that, in fact, you could use for particle board or other things, right? So, we're talking about a subset of residues that aren't used for making any wood products at all, right? And those other residues are not high quality things to burn. In many cases, they have moisture content or tar or other issues. So, and a lot of people want those residues. Right now, the world's getting a lot more because we don't have an excess of land, right? We're not going to be able to have as much waste as we have had in the past 10 or 20 years. We are going to get more and more people are focused on using every last scrap of, useful wood from forestry and using every last useful thing from agriculture. And by the way, you can't just scoop up all of the agricultural residue because a lot of it had been used to sit in the soil, right, and put carbon back into the soil. So, I get very worried. I'm not worried about small scale things. I'm worried when people say this is going to scale up really, really big, but it's not going to have any side effects. You can't, we're talking about 50 billion tons of greenhouse gas emissions a year, right? And 40 billion of those came out of carbon that was buried in the ground, and it was dense, right? You trying to put that back somewhere, that is a very, very big challenge. And trying to take it up from anywhere that's lying on the ground at that scale, clearly nature was dealing with it, right? It didn't have no use to the world. It may have no use to us in the short term, but that's not different from saying it didn't have any use to the ecosystem.
Next question. Can you discuss how wildfire, which results in loss of forests, is impacting the issue of bioenergy? In the United States, forests are being thinned to reduce the risk of catastrophic wildfires, and this wood is being used for bioenergy. Do you think forests should not be thinned? If they are thinned, what should be done with the harvested wood?
Well, I think that's a pretty straightforward question. Clearly, if you thin the trees and burn them, your net benefit is reduced, right? The point was you're trying to avoid getting, the point is, right, you're trying to avoid the wood being burnt. It can't really be the best climate strategy. I do understand, yes, I understand there's a big report that's going to be coming out in the not too distant future, which is going to say that this is a good idea. But thinning is definitely a worthwhile strategy to pursue. I want to make a pretty clear point, though, that is a big difference between saying it's a worthwhile strategy to pursue and you telling me that if I cut down this many trees and burn them, I'm going to reduce the chance of wildfire this percentage over this area, right? Because you're telling me now that it's better to do what you just described than something else. So that would be point one, right? It's a total difference between making a hand-waving argument, oh, we need to thin trees, and therefore let's thin a lot of trees and burn them for biomass, right? Those are two different statements. The second thing is that we're going to need a lot of wood products, right? And it is clear that deforestation for wood is not a good thing, right? So the answer to the question, what would I do with the thinning of forests, is I would use them to make forest products so I don't have to cut down actual forests to make forest products, right? Again, again, at the small scale level, that's a different matter. But at the large scale level, if you're talking about hundreds of millions of acres, right? You need hundreds of millions of acres to make a dent in the CO2 problem, right? So are we thinning the equivalent of the little areas around the trees that add up to 100 million acres? Well, if we were, that would mean that there's 100 million acres of forest product trees we don't have to cut down. So, this gets to the opportunity cost issue, which is just not addressed enough. The question is not whether you can take those thin trees and burn them and get something out of it. The question is, what is the best thing to do for the climate, right? Because you're cutting those trees down to protect the forest from wildfires, right? But cutting the trees down and burning them also is a cause of global warming, right? You're not thinning the trees because of global warming. You're thinning the trees because of the wildfires. And you may say the wildfires contribute to CO2, but again, unless you can quantify all of that, you're just making a hand-waving statement. The bigger question is, to the point, is there a better use for that wood than going through this bio and burning it? And the answer is yes. I don't think analytically there is any question there's a better use for it. And there will be in 10 years when the world needs more forest products. And there's some people who argue, and the analysis shows, that if we in fact replaced more steel with wood, we would actually lower CO2 emissions. So this is a very complicated analysis. We do need more wood products, a lot more than we need more burning trees for bioenergy.
Next question. If there's siting issues that can seriously inhibit the scalability for CCS build-out, would the same not be said for transmission line build-outs for a fully renewable and larger grid? Would the takeaway there be against CCS or for an all-of-the-above approach to mitigate hedge for some issues jeopardizing given solutions across the board?
Well, it's a very good question. I think that I would be the first person to say that scaling up anything, solar, wind, you name it, to the levels that we need, right, to address climate change, that's going to have impacts. I'm not be the last person to say that there's any one of these a silver bullet that doesn't have impacts. The scale of what we need to do is simply too large. I think the question you have to ask yourself is, again, it's a cost-effective issue and it's a practicality issue. A lot of I think that what people are going to find when we really get serious about transmission is that you can rewire a lot of transmission and deliver more juice. And if we used digital, we don't use the full transmission capability because the grid isn't smart enough to do that. And there are people who know this a lot more about me. And there are also a lot of technologies that are coming along that allow you to use the renewables locally, right? So there are people who are developing technologies, for instance, that can replace industrial heat with renewable electricity. You don't need the grid if you can build the renewables right there. The issue on the siting and like I said, if you have a CCS, if we crack, solve the commercial scalability of CCS, you don't have to worry very much about the siting issue if you put them on existing fossil fuel plants, right? That's very straightforward. Now, if you say to me, I'm going to put it on a direct air capture system, well, this is a challenging siting issue. And by the way, there was a debate between Howard Herzog of MIT and David Keith that you can find online, in which Herzog says, people say the siting issue of direct air capture is easy because you're just pulling the CO2 out of the air. But in fact, it isn't easy. It's really hard. And Keith had to concede that point, because if you're going to site direct air capture, right, you certainly are going to want to avoid long pipelines, right? If that's right. But that means you got to put it near the place you're going to deposit the CO2, right? Okay. But you also need pure maximal renewables, right? So it's got to be a place that's near the storage. You can deploy large amounts of renewables, and also it's got to have access to the water and all the other infrastructure, right? You can't put it in the middle of nowhere, right? That will be problem. It's not problematic to do one plant, but to scale it up. So the point is that yes, siting direct air capture is problematic, and some direct air capture plants actually model that they're going to use the waste heat from industrial facilities, right? But again, most of those facilities aren't near the storage, right? So if you say, I've got to put this in a place near industrial facilities and the storage and an abundant supply of renewables, right? Well, I've narrowed the world of where I can put scalable direct air capture to not many places. And so again, I just urge people, what I'm trying to do in these analyses is really look at the practical issues, because the practical issues in the energy business are the reason why we don't actually see a lot of rapid change in the energy world, right? Every single thing we are doing today that is at scale, we have been working on for 50, 60 years or more. So the notion that you're going to take a technology that is not commercial today, and you're going to A, successfully make it commercial, and then B, scale it up, and tell me this is going to happen in 2 decades, that is so far beyond the history of the world that, again, it's not impossible if the world got desperate about climate change, which it should be, but that's not the world we live in yet. And so I think you're saying we can't afford, I don't just think we need to focus our money on the stuff that we know works cost effectively and solve those problems, rather than saying, oh, we're going to pick this unproven, uncommercial technology that may or may not be scalable, and say, oh, yes, it's got this other problem of siting and pipelines, and we're also going to solve that one too, right? That's a lot in a world that really should be desperate, right? Want to get down to near zero by 2050. So, and by the way, I don't want to say like I'm not against pursuing R&D. I ran, the largest R&D program in the world for all of these technologies when I was at the Department of Energy in the mid-90s. So R&D is really important, but saying that you're going to scale up in the next 10 or 20 years as if you're a comparable solution to solar or wind, or even coal with carbon capture and storage, I think that is magical thinking.
All right, let me conclude with one last question to pin you down a bit about this. Okay, so analysis of Back's forests and direct air capture. Is your fundamental conclusion that all three of them are per se untenable and should not be pursued, right, from a standpoint of sustainability, economics, whatever metric you're using, or that they have a role, but at an extremely small scale, right? Because there's a fundamental difference
Right.
between those two as we think about portfolios. Where do you come down?
Well, you know, uh, the International Energy Agency published last month, or I guess it was the end of September, their 1.5 degrees Celsius scenario, which they do every year, right? And they, in the last since 2017, they have scaled back the amount of BECS from 5 gigatons in 2017 model, which was a 1.5, I think the 1.75 degrees Celsius or 2 degrees Celsius scenario, to about 1 gigaton. They have never had. They're sitting around 700. 0.7 gigatons and this is 2050. 0.7 gigatons of direct air capture in 2050. So that's 1.7 gigatons. So if you were to tell me that we might, if we spent staggering amounts of money and weren't so concerned about the opportunity costs, or we spent the right amounts of money on everything else, and we did this, and we got to up to a gigaton, I wouldn't say that's impossible. The physicists, they're not going to say it's impossible, but is the number going to be 3 or 4? That strains credibility, and it wouldn't be a good idea. Okay, and on bioenergy carbon capture and storage, you could put carbon capture and storage on every existing bioenergy facility, right? So that would capture some CO2. That would get you, maybe it depends how you do the analysis. It wouldn't get you a gigaton. It might get you close to a gigaton. Is it the best use of carbon capture and storage? No. Would it be better to phase out bioenergy like corn ethanol rather than, putting on carbon capture and storage on biorefineries and capturing one of the 3 carbon atoms? No, it'd be better to stop doing corn ethanol. But, we don't live in that world. So yes, you could put CCS systems on existing bioenergy plants and capture some stuff. So if you were to tell me between bioenergy carbon capture and storage and direct air capture, we could get a gigaton and a half in 2050, I would say we might. It would be expensive. I think those would be the most expensive tons. I don't think that would be the best thing to do. But my point would be, we've got 50 to do, right? So the notion that people had, there was a model, back in the IPCC's, I think it was 1.5 degrees Celsius paper, of 20 gigatons, right? No, that's and then it went down to 10. And in the mitigation report, 2022 mitigation report, they finally conceded, we've wildly overscaled this number. So yes, again, as I say, the R&D is worth pursuing. The cheaper things, the things that are more promising, are worth pursuing. Could one of them break out? Anything's possible. Should I plan any of my modeling on that? And therefore, should I say, oh, I don't need to do as much of the renewables because this stuff is going to save us? No, that would be a very unwise decision. Trees, look, the first thing we need to do on trees is stop deforestation. People talk a lot about planting trees. When we do go about planting trees, unfortunately, we usually plant monocultures, right? You can Google that one. We don't we don't go out and say, what is a sustainable biodiversity, right, that also captures CO2? That's not what happens. What happens when you do a major tree planting effort is the people involved say, how do we make money? So we're going to plant, we're either going to do a fast growing monoculture, right? Or we're going to do trees that, like coca trees, or, what trees that you can make money from. Those are not, however, the ones that maximally store carbon. So analytically, this is a challenging thing to do, because you can pretend that you do it the right way, and you can pretend that there's all the land in the world, and you can come up with a number and say, that's nice. But, to do it in the real world the right way, without screwing over lots of people or the biodiversity. These are really hard things to do. Should we plant more trees? Absolutely. Should we first start by stopping deforestation? That would be the best thing to do. So again, trees can get you something, but like I said, it's of the order of what the other number I was talking about, a couple gigatons. I think you could get in a perfect world, but that perfect world requires you to stop deforestation, right? Otherwise, your tree planting is only making up for the tree cutting down. So you're talking about what's the net benefit of a thing I can do, right? So I think that's the state of affairs today, and it's certainly of the right order. Could it be twice as large? I think practically it would be hard. Maybe not impossible, but I think it would be a mistake to try until you've done all these other things, right? Until you've replaced, the fossil fuels on the grid, until you've mostly electrified the transportation you can, until you've replaced, natural gas boilers with heat pumps. You got to do most of that before it's worth spending the staggering amounts of money you would need on DACs to get the numbers that people talk about. So that's how I'd look at it.
All right. Okay, we are going to end it at that. And once again, I'd like to thank you, Joe, for your thoughts on this and audience engagement. These are issues for us to be thinking about moving forward, right? Questions of opportunity costs, questions of sustainability, scale, and equity and justice, right? Which should always be first and foremost, and people may disagree on, but are critical questions. I agree, especially notions of opportunity cost. And so, thank you once again, Joe. We are